In this video, we're going to extend our knowledge of classes inside of Python and Rhino through an exercise demonstrating a cellular automata in Rhino. Like LinkedIn's Ant, cellular automata date back to some of the origins of programming. One in particular, John Conway's Game of Life, is an example of cellular automata and his attempt at structuring a CA which can simulate the biological production of life and death. I'm going to open up a page and we can take a look at the rules that John Conway laid out for his particular version of a cellular automata. So this is John Conway's Game of Life. The Game of Life, also known simply as Life, is a cellular automaton devised by the British mathematician John Horton Conway in 1970. It is a zero-player game, meaning that its evolution is determined by its initial state, requiring no further input. One interacts with the Game of Life by creating an initial configuration and observing how it evolves. So like LinkedIn's Ant, we have this kind of involvement or correlation with emergent behavior or emergent properties. We see a couple of examples of these emergent properties throughout this page. If we just scroll down though, the primary thing I want to focus on are the particular rules for the Game of Life. So if we read this rule section, we'll see that the universe of the Game of Life is an infinite two-dimensional orthogonal grid of square cells, each of which is in one of two possible states, live or dead. So already, if we think back to the LinkedIn's Ant example, live or dead could also be black or white, 0 or 1, or true or false. So we have a binary action state in this example as well, just like we did in LinkedIn's Ant. So then also it's suggesting or populated, unpopulated, respectively. Every cell interacts with its 8 neighboring cells, which are the cells that are horizontally, vertically, or diagonally adjacent to that particular cell. At each step in time, the following transitions occur. Any live cell with fewer than 2 live neighbors dies as if by underpopulation. Any live cell with 2 or 3 neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies as if by overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. The initial pattern constitutes the seed of the system. The first generation is created by applying the above rules simultaneously to every cell in the seed, live or dead. Births and deaths occur simultaneously, and the discrete moment at which this happens is sometimes called a tick. Each generation is a pure function of the preceding one. The rules continue to be applied repeatedly to create further generations. So we can see here generation 0, population 5. I guess we should reset, and then we can just step by generation 2, 3, 4, and we start to see reproduction occurring as well as death, and we get an evolution of whatever our population is. I'm not going to get too much into this at this point, but maybe at the end we'll come back to this. But there are some known sample patterns that in the initial configuration will produce certain kind of repeated patterns. So you have still lifes, which are kind of still configurations that are entirely stable. You have oscillators that will oscillate between certain states, but set states. So here you have a 2-period oscillator for the blinker that just goes from horizontal to vertical. For the toad, you kind of have this Tetris stack that then opens up and closes. Or the beacon, you have 2 solid cubes that erode at the middle and then come back. So each one of those flickers between a set of states. And then you have spaceships, which are actually able to move across the environment. So a glider is maybe the most famous one, but it's this kind of sequence of cell states that is able to actually move across space, and it does so in a stable way. These are things that we can reference back to if we want to produce certain effects in our cellular automaton. And if we wanted to get any of these, all we would have to do is look at the kind of initial state of any one of these, or replicate in our initial state any one of these configurations. And then we would be able to get those to show up in our own cellular automaton. In our example, we're going to start with a similar setup to our LinkedIn's ant. This time, instead of starting with a seed state of an entirely black mesh plane, we're going to start with random values. That's just because we might not be so familiar with these particular rules. So instead of confining ourselves to engaging with this, we're going to just make ours run. And then later on, you would be able to replace this random starting state set with a particular one based on maybe some of these, and you would do that just like we did in LinkedIn's ant example. So to get started, we'll open up a clean Python script, and inside of this, I'm going to leave a multi-line comment saying introduction to Python classes, cellular automaton, and then I'll leave on a different line John Conway's Game of Life 2D. At the end of this video, I'll show briefly how to adapt this into a three-dimensional array. So it's not a 3D cellular automaton. There are ways to do that are very similarly structured. But what I'll show is just how to store the output data from a 2D CA in a three-dimensional way. And there are reasons why you would do one of either, I suppose. So a three-dimensional CA that operates through two-dimensional generations has more continuity between the kind of three-dimensional features across layers, meaning the movement present in the CA in 2D is then present across one axis in 3D, whereas a 3D CA you might see more kind of chaotic motion or random motion. At least to my eye, I would describe it as chaotic motion. And now it is happening within a 3D feature space, so you do get more complex motion as well, or more complex interaction. The way we're going to start, though, is very similarly to our LinkedIn's ant setup, operating on a mesh plane inside of Rhino space. So I'll go ahead and start by copying and pasting the rules that we just read through as well, and I'll just separate these onto separate layers so that we can go through and read them. Okay. So we have listed out for us here, the universe of the Game of Life is an infinite two-dimensional orthogonal grid of square cells. So this sounds pretty similar to LinkedIn's ant. So we're going to just go ahead and default to a mesh plane. So we're going to make a mesh plane in Rhino, just like the LinkedIn's ant example, starting at the origin, a X and Y density count of 100 cells in either one, and a length of 100 and a width of 100, so that each of our vertexes are spaced by 1 unit. Since we know that we're operating inside of Rhino, we need to import our Rhino script syntax library as rs. And since we're in our class introduction, we know that we'll likely have some class which we can just automatically refer to as cellular automata or cellular automaton. Let's just say automata. For now, we'll just leave a pass since we don't actually have any information to input into here yet. Okay, so if we read again back through that initial description, we know that we'll operate on a mesh plane or something similar to a mesh plane. And then if we read that next line, each of which is in one of two possible states. So again, very similar to our LinkedIn's ant, live or dead, or white or black, or 0 or 1, or true or false. Every cell interacts with its 8 neighbors. Okay, so that's where we're going to stop for now. So we'll just take this first section first and build up the kind of base environment for our CA. So we have a mesh plane in Rhino. We need to get that into Python. How do we do that? rs.getObject, and then give ourselves a message, select mesh plane, and then add a filter of mesh. Okay, now how do we get that from just a reference inside of our Python script into our CA? Well, we need to pass it in using a constructor, and we need to instantiate one instance of our class Cellular Automata. So I'm going to call this myCA. We're going to set this equal to Cellular Automata, and we're going to feed in our mesh. At this stage, I'm going to copy this down, give ourselves a line break, comment this out, and paste that. Okay, so now inside of our CA, we know that if we want to pass in information, we need a constructor function, and for any function, we need to refer to self. Now I'll just say pass inside of there. Okay, and we can't just refer to self if we want to pass in information. So we know we want to pass in our mesh. So let's just pass in that mesh ID, which is the output from our get object. Inside of this constructor, instead of pass, we can now save this as a property in our class Cellular Automata. Self.id equals mesh ID. So far we've just dealt with the kind of management and basic setup of the CA relative to our mesh plane inside of Rhino. Now we want an array of cells. So like we did in the LinkedIn Xant, our array of cells is just going to be our self.vertexes of the mesh. So rs.mesh vertices of self.id. So those mesh vertexes stored in their own list. Now when we keep reading through that description, we also see that we have to save out a set of states. So again, very similar to the way that we were operating inside of our LinkedIn Xant. So states for each cell. How do we save out these states, or what are the constraints of these? We need them to be the exact number of cells that we have, which are the vertexes. So we need to say self.states equals, and we can start with just an empty list, but then we know already that we need to fill that list, and we can fill it for vertex in self.vertexes. So the amount of vertexes that we have, self.states.append, and we'll go ahead and just start with false for now. Now I'll copy this down. Okay. So if we wanted to infill these states, not just with false values, but we actually wanted to create a random value of each one of these states and then append it to the list, we would need to first import a separate library, which is a library called random. And instead of appending false, we can append either a 1 or 0 value by using random.randint, which stands for random integer. And if we take a look at the randint function, it takes in an A and B value and then outputs a random integer in that range. Well, we only want either the integer 0 or the integer 1. Well, how can we do this? We can give it a random range of 0 to 1 and append that to our self.state. The next thing we want to do is see if this is actually working. So I'm going to just copy this, we'll paste it down. How can we see that this is actually doing something? First, we can just check if there's an error. So hit play, prompts us to select our mesh plane, and we don't get an error, but we don't see anything either. In the LinkedIn Xant example, we actually made a function to render. So why don't we just go ahead and do that. Def render, input self. And now we need to create a list of colors based on the state values. So this is the exact same operation as our LinkedIn Xant. So we need to start creating a list by creating an empty list, and then for state in self.states, looping through each one of those. We need to check if state. So if it is true, so that's just shortened for if state is true, Then colors.append rs.createColor, just like we did in the LinkedIn's Ant example, and then feed in a value of white, which is 255, 255, 255, else. So if it is not true, then we're going to just copy and paste that line and change these to 0, 0, 0. Again, you can change these colors to anything you want. It's just a way to visualize this for us so that we can actually see if it's working or not. Now we need to store colors as vertex colors on mesh. How do we do this? We call rs.meshVertexColors, which allows us to input a mesh using self-ID and then a color list colors. And then one last thing we want to do is we want to ensure that every time we update this, we actually draw it into our Rhino document viewport. We can ensure that by saying rs.redraw, which is just going to redraw our viewport and make sure that whatever we've updated has been rendered. So the next thing we have to do is actually call this function, which we can do for now inside of our constructor. So we can just say self.render. And now if we click play, select our mesh. So if we're using 0 and 1 values, we can still use them in the same way as true and false, but we just can't say equals true. So we just need to make sure that our state value here is just set to if state. So when we click play and select, a random set of values get stored in our mesh plane. And we're rendering just inside of our constructor function for now, which is fine because we're just rendering out that random value on our mesh, which is okay to start, but eventually we're going to place that call inside of a function that actually is performing the kind of operations of this cellular automata. I'm going to go ahead and select all of these layers, comment them out, paste below, and we're going to jump to the next step. So in this step, we're going to actually build the primary function which will perform the running of the cellular automata. In order to do this, we need another function which we're going to call run. We know we need to feed in self, so for now that's all we'll have. Inside of this function, if we translate the rules from John Conway's Game of Life, we know that we have a for each state get neighbor states rule. And also we might want to note that we have 8 neighbor states, which is the immediately adjacent and diagonal neighbors from each point, in this case on this mesh, but in the 2D array. Next we have any live cell with fewer than 2 live neighbors dies. And then we have any live cell with 2 or 3 live neighbors lives on. Any live cell with more than 3 live neighbors dies from overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction is John Conway's analogy there. Okay, so we know that anytime we want to run a function inside of a class, we'll add a pass here as well, we will have to call that function outside of, or from somewhere. It doesn't have to be outside of the class, as we see here in our constructor calling a function inside of the class itself. In this case, we are going to call it starting from outside of the class. So I'm going to call my CA, and then we just need a period and then the name of that function, run. And right now we don't have any inputs, so we'll just open and close those parentheses. Now, if we're going to tell this to run, but we don't want to nest this into a loop, then we need some other way of, 1, making it continue to run, and 2, telling it for how long we want it to run. So we're going to structure something fairly similarly to the way that we structured recursive functions by making a call to the function itself from inside of the function. We can do this, just like with the recursion example, by setting an iterations, or let's call them generations, value. And this generations we can start with as 10. Now we need to pass this generations input into the run function, and then we need to read it into our run function. So we can call it underscore gen. And then in order for this to actually operate recursively, we then need to call the function, not referring to it as my CA, but now that we're inside of the class, we need to call the function by self dot and then its name. So self dot run, and it's going to take in underscore gen. If we just feed in gen, this is going to loop forever. So we need to be sure that we're feeding in a -1 value to subtract 1 from the generation each time we iterate through. And then we also need, as I mentioned in the recursive functions video, we need a test or a conditional to limit us from running this forever. So in this case, we're going to say if underscore gen is greater than 0, and then we're just going to nest that run inside of there. So it's going to continue to run for those 10 steps of the 10 generations. Eventually, it will then get to 0, and we can test this just by typing print underscore gen. Now, once we do satisfy that condition, so or else, so if that condition is no longer met, then we're going to pass out of the function, and we can do that by just typing in return. It will stop the recursive running of that function when that condition is no longer met. If we click play, select our mesh, we can then see our generations go from 10 to 1, and then at some point it becomes 0, so that next step it becomes 0. 0 is not greater than 0, so that's no longer met, and we don't print our gens anymore. Okay, so now we can go ahead and copy all of these lines, comment them out, and then we'll go on to the next step. The next step is going to be translating some of those kind of pseudocode rules from John Conway's Game of Life description into actual rules to operate or run this CA. The first one we're going to tackle is getting the neighboring 8 states. To get the neighboring 8 states, we first need to loop through every single state to get the current state, right? To get each state in the list of states. So we can do that by saying for I in range length self.states. So that will start the looping through of all of our states. And then inside of here for each state, so I'm going to just nest that comment inside of our loop, because for each state in our list of states, we need to test for that particular state or that particular vertex's neighbors and all of the conditions for those. Since we know that we're storing all of our neighboring states, we're going to start with an empty list called neighbors, and we're just going to set that equal to an empty list. So the name neighbors equals to open and close brackets will give us an empty list. Now we just need to fill this empty list with our 8 neighbors. So we'll say N1 for neighbor 1, N2 for neighbor 2, and we'll just keep going through here until we get to 8. So now we just need definitions for each one of these variables, neighbors 1 through 8. So we know that we'll use our self.states list. So in order to test our neighboring states, we're going to need to refer to self.states. So if we wanted the current state, we know that we would use self.states of I, right? So of index I, whatever that might be. If we wanted the next state in our list, then we would just want I plus 1. If we wanted the prior state, we would say self.states of I -1. Now the tricky thing here is to start to structure the array from the list that we currently have that allows us to cut this list into a series of rows. So we don't just need the next state and the prior state, we need the next state. So let's think of it as the state to the right, the state to the left, the state to the top, bottom, and the four corners. In order to do that in a flattened list, what we need to do is use the density of the width versus the length, right? So the count in the width versus its length, which we have 100 by 100. So that would be an array length of 100. So if we make a variable up at the top, we'll make this a global variable in all caps, and we're going to set this equal to 100. The important thing to note here is this value must be equal to the mesh density. So in each of the X and Y axes, this value must equal the count in those. For this particular example, now there's many ways that we can make this more versatile and adaptable, but for this particular example, that array length must equal the X and Y count. They all must be the same. So the reason why we structure this within array length is because the entire length of all of the vertices is going to be that density 100 times 100. So we're going to get 10,000. So 10,000 total vertices, and we can test this by just saying print length self.vtx. If we run this, we're getting some errors here, so I'm going to just comment those out. If we run this, select our mesh plane, we get a printout of 10,201 actually, and that's just because it's 101 in each axis. So if we change that array length to 101, then we have the appropriate number. It's 100 faces in each axis is the way that Rhino structures meshes, but then there's an extra one vertex, so it's going to be 101 on both axes. So now that we have that 101 value set as our array length, what we can do is we can break up our list of 10,201 into chunks of size 101, which is a way of constructing essentially rows. In order to do that, all we have to do, instead of saying self.states of I plus 1, say self.states of I. And if we just wanted not our current position or to the right or left, but to the top and bottom, we would say our current position I plus that array length. So plus, and then just that variable array length. So that's going to give us exactly our position plus 101, which gives us the point above us. Now if we copy that same thing, but then said minus array length, that gives us exactly the point below us. Well, now if we wanted the points to the right and left of those, so if I just copy these down here, we'll kind of put these at the middle, I suppose. So we'll do 4 and 7. So those are the two top and bottom points. And then we just need the points to the right and left of those. Well, we can just copy those. I'm going to space them out in groups of 2, so the right and left of our current position, and then the top set, and then the bottom set. The points to the right and left of the top and bottom set are just I minus array length plus 1, and then I minus array length, and then I minus array length minus 1. So that gives us all of the neighboring 8 vertices. Now, one last thing that we have to consider here is what if they're on the edge? Well, if we were to give it a vertex that was on the edge and then say I plus array length, or I plus array length plus 1, which we need to add here as well. So those should match, just minus array length and plus array length. So if we were to add a point here all the way at the corner, we no longer have an index higher than that value. So that would be the highest value index. So we'd get an error saying, we need to change the index value and lower it. One way we can do this is we can check and say, is this bigger than our length of states? But another way, which actually allows us to operate with these kind of chunked out rows of data, is to say, instead of taking the index of I plus 1, take the index of I plus 1 modulo length self dot states. Now what this does is it basically breaks it down and says, if it is one index higher, divide it by the length of states and take that remainder and use that as the index. What this is essentially doing is it's making a kind of toroidal space which allows us to map from the edges across. So we go from the edge across to the other side, and then we continue on. So instead of stopping at those edge values, we're able to kind of continue that space. So I plus 1 modulo length self.states. And then we'll just copy this same thing for all of these. So I minus 1 modulo length self.states. And then all of this needs to be in parentheses because we want all of that modulo length self.states. Okay, now once we've set that, we just need to bundle all of these values into one list, which is going to be called neighbors. We can take that list, since we're storing values inside of here after, we could either append each one separately, or we could just directly say neighbors equals n1, n2, n3, n4, n5, n6, n7, and n8. So we're directly storing into our neighbors list instead of even needing that empty list to start with. So any live cell with fewer than 2 live neighbor size, any live cell, any live cell. So it seems to me like we have 3 conditions that can be nested under if self.states of I. So if self.states of I, then, and now inside of here we can nest all of these conditions because they all require our cell to be live. And then we can say else, and now we can have our condition for any dead cells. And we only have one rule for dead cells, so we might as well go ahead and get started there. So we want to check whether or not our neighbors list has exactly 3 live neighbors. And if that is the case, then we will flip this value from false to true. So in order to do this check, we need to say for n in our list neighbors to search through each one of our neighbors. And if n, so if n is alive, then alive plus equals 1. Now what this is going to be is a count of how many of our neighbors are alive. So now we can make this variable above and say alive equals 0. So if we have exactly 3 neighbors alive, so if that variable equals 3, then change state to alive. So if it equals 3, change state to alive. So that's the exact translation of any dead cell. Yes, we're qualifying that in the first conditional with exactly 3 live neighbors. We're fulfilling that with our loop through the neighbors to check and count how many are alive. Now, if we were to update or override our self.states here, then what would happen is as we check all of our other states in all of the other cells, we wouldn't get a kind of accurate representation of that particular generation. So what we need is a temporary list which is going to satisfy or equal our self.states. So we can call this our next states. We can start by setting this equal to self.states. So we'll start in the run function, setting that equal to self.states, and we'll use this as a temporary list that we can infill or replace items in while we're actually looping through here each one of the items. So I'll say next states of I, and then we can set this equal to 1. So next states of I equals 1. Now, if we're using next states, we know that when we go to run this again, we actually need to go ahead and save our states as those next state values. So once we're done iterating through all of our states, then we have to save that back into our properties of our class. So we do that right before we call the run again. It's important though that that doesn't happen inside of the loop. Otherwise, we'll get a kind of very confused version of what this CA is supposed to be, because every state is constantly going to be updating all throughout, and we won't get them updating based on what their state actually was coming into this. So now we can jump up to the alive cells, and we can start structuring these conditions as well. So just like with our dead cells, we want to check for how many are alive using alive equals 0 and then for n in neighbors. And we can say if n alive plus equals 1. But some of our rules actually care how many dead cells there are. So we need to say else, if it's dead, dead plus equals 1. And then we also need a variable for dead, which starts at 0. Now, in each of our conditions, we have to go through and test for these particular ones. So if any live cell, yes, that's what we're in that condition, with fewer than 2 live neighbors. So if alive is less than 2, then self.states of I equals false, 0. And then our next condition here, any live cell with 2 or 3 live neighbors lives on. So we don't actually need to tell it that it lives on, but if we wanted to, because we're not actually changing the state, but if we wanted to, we could say if alive equals 2 or alive equals 3, then self.states of I equals 1. But it already equals 1, so we don't really need that. But just for convention to kind of map these exactly. And also, this is not an if statement, but rather an elif statement. So then finally, if any live cell with more than 3 live neighbors, any live cell with more than 3 live neighbors dies. So here we just need to check if alive is more than 3, so greater than 3, then self.states of I equals 0. So if there's fewer than 2 or more than 3, then we have these responses to flip those particular conditions. Then if we go all the way to the bottom here, we're updating our states. We're running for X number of generations. The last thing that we need to double check is that our self.render is now being called inside of our run function rather than our constructor. And it is. So now we should be able to go ahead and hit play. And we should see this run for 100 generations with each of the cells responding to their neighboring conditions. And this is a random start, so we're not going to see so many of those stable configurations, but we do see a little bit more kind of patterns being recognized in the later stages of these generations. And you can see there are certain kind of repetitious elements all throughout, and it's a little bit less random than when we started. To finish our video introducing Cellular Automata using classes inside of Python, we're going to rebuild a very similar structure to our 2D CA, which we're seeing visualized, or at least the initial state, visualized inside of Rhino via a mesh plane. But this time we're not going to use a mesh plane at all. We're going to rebuild that same structure using an array of points, or a grid, a 2D grid of points. So first we have to build that grid of points. Then we're going to change the render definition to not change the color on a mesh, since we won't have a mesh, but to actually add a box for every live point that we have in our CA. Now, if we did this and we just kept our generations as the exact same amount of points, or exact same points in space, we would just get a kind of static production of boxes in the same locations. Now, they might flicker where some generations, they're built in some places and not in others, but we would see them basically duplicated in generally the same places. If we want to make this a three-dimensional stack, so think a kind of 3D tower that takes the 2D CA and then somehow builds in a third dimension, how would we do this? Well, we actually already have it not running in 3D, meaning not checking the neighbors in 3 dimensions. It's still checking the neighbors in 2 dimensions. But what we had in the previous portion of this video is we had movement on our mesh plane. So if this mesh plane that we're looking at right here, if this is representing 2-dimensional data, then when we have it move in this kind of video animation, that adds another dimension, right? So if we consider time an additional dimension to our 3-dimensional space, in this case we have 2-dimensional space plus time, so each time frame being a different dimension, which adds that third dimension. How can we take advantage of this? We can increment in the z-axis 1 unit for every single time frame, meaning every generation increases in the z-axis. What do we result with? We result in a growing tower formation where each layer of the stacked boxes in the tower represents 1 generation in the 2D CA. So we'll see what this ends up looking like as an output from this portion of the video. But same basic principles, but we're going to just go ahead and start with a fresh Python file just for the sake of, reestablishing some of the ideas in the prior video. Since this is building directly upon those logics though, there are portions in this stage of the video that I'm going to kind of glance over very quickly or skip through since we already discussed that in the first part. So feel free to go back to that first part and find where that logic or where that kind of method was talked about if you feel the need to go back through it. What I'm really going to be highlighting in this part of the video are the differences between the logics of this 3D kind of output from the CA versus the 2D representation that we had in the first portion. To go ahead and get started, we don't need this mesh plane. I can select this and click delete, and we can just have a fresh space inside of Rhino. And instead of top view, I'll switch this to our perspective view so that we can actually see the 3D formation as it happens. Also, I've gone to File and New and opened up a clean Python file. At the top, we can just say Introduction to Python Classes, John Conway's Game of Life, 3D Cellular Automata Representation. Close out that multi-line comment, and then we'll go ahead and get started. So like with any script, start interfacing with our Rhino environment, we need to import Rhino script syntax as rs, giving it that nickname of as rs. Just like in the previous portion of the video, we need a class, which we can call Cellular Automata. And since we've already covered this, we're going to just jump right into building our constructor since we need inputs into this class. So our constructor function is going to, right now, just have self fed in, And we'll see if we need anything else, but again, the structure is slightly different for this portion, so we're not going to need to feed in a mesh plane, but let's see if we need something else when we kind of go further into building this. I can say pass for now, hit enter, and then we just need to construct an instance of this CA. So I'm going to call that my CA, just like we did last time, and call an instance of that class. So call that class to construct it, and the instance is stored in my CA. Okay, so that's how we're going to go ahead and get started. And now we can just comment this out, add a break, which again, this is just a visual comment so that we can see the kind of breaks in our script. And then below this, I'm going to paste those lines. Okay, so inside of our constructor, what we're going to need are not vertices like we did with the mesh plane, but a list of points. So self.points equals, and this list of points is going to start empty. That's because we actually need to build our list of points. We don't have points inside of Rhino, we don't have points or vertices from a mesh plane, but we know that we're going to need those 2D cells for our CA, which we're going to use points. So we have an empty list called self.points, and then we need an empty list called self.states, just like in the previous video. To infill data into both of these lists, what we need is a nested for loop to go through and create a point array. So how would we create a 2D array of points? So if we go into Rhino, draw a point, we can start with it at the origin, and then we just wanted to make an array of these points. Well, we would start with looping through items or numbers in the x-axis, and we can change those point values so that the x increments. And then once we've done an entire row in the x, then we would want to iterate through that same x transformation, but now one step further in the y, and then another step further in the y, and so on until we have a 2D array. So what this indicates, like with the kind of math curves or thinking through those initial nested loops that we covered earlier in previous videos, we're going to want a nested loop to be able to construct a 2D point array. So our nested loop is going to actually be stored or placed inside of our constructor function. And the reason why it's placed inside of our constructor function is because we just have empty lists, and we need those lists filled to be able to start with our cells and states in the starting point of our CA. So to kind of build this setup, we need to start with an array of points and an array of states. So for our nested loop, we just want to say for I in range. And inside of this range, we need to input some variable, which is going to be the width. And then we also need a height of this array, or the number in the x-axis and the number in the y-axis. This is basically going to be the density of cells in our CA. So what I want to do is just make a global variable up at the top in all caps, which means it's accessible inside of any function or class. So this global variable is going to be called array_length. And we can set this equal to 20 to start. Now I can copy that array length variable, and now we're going to loop through 20 times for I. And we could even say, actually, let's call this x, and then let's call our next one for y in range. And here we want our y dimension or y density to be the same as our x. So we're going to loop through that same value array length. So what do we want to do with this? Well, what we want to do is create a point, not add it to our document, but just create a point. If we wanted to test that this is actually working, we could maybe start by adding the point, but then we can change this to create point so we're not creating new points every single time. So let's start with add point. And then inside of here, we just need to feed our x, comma, y, and then comma 0. And we're feeding in 0 because we want to start with that CA just on the XY plane at 0 in the Z axis. So if we go ahead and run this, already we're calling and instantiating that class, we're running the constructor function, we're creating 2 empty lists, and then we're looping through to add those points. If I hit play, we should see it making that 2D array of points, which we do see it doing. So we have our 2D square grid of points, which is great. It's visualizing inside of our Rhino file. We can keep that visualizing for now just so that we have some checkpoint until we build up our render function, which is going to visualize it with 3D boxes. But before we move forward, what we need to do from here is actually append this to our list of points. Now, what we could do is just say self.points.append and directly add those points. But this would give us a one-dimensional list of points. That's perfectly fine to do. We can do it that way. We use this for the vertex arrangement in the 2D CA, so we could do that and it's totally fine, and then we could just be done. But since we have a nested loop here, we already are creating rows in the X and columns in the Y. So we're already separating our singular list into 2 axes there. If we want to take advantage of this, what we can do inside of the first loop is say points row equals empty list. And since we want to append to our states as well, we're going to say state or states row equals empty list. And now inside of our while loop, not self.points append, we can say points underscore row dot append. Now what this does is it steps in to the X. So we're going to be at 0x, loop all the way through our Ys, make an entire row, or I guess in this case column in the Y axis. And then once we've made that column, it clears the row definition, and then we move on to the next one. So we're creating blocks of rows of points or columns of points instead of just appending it all to the self.points. Now we can do the same thing for states row dot append. What do we want to append here? We want to append a random value, either 0 or 1. So we can say random.randInt for that random integer value, and then we need to give a range here from 0 to 1. So an integer ranging from 0 to 1, so either 0 or 1. In order to use that, we need to actually import the library for random. So now we've imported RhinoScript syntax and random up at the top. Now if we left this like this, what would happen is every single time we're incrementing in the X, we would just clear out those lists and we would end up with just the last row for both the points and the states. If we want to add this to our main list, which are self.points and self.states, what we need to do is take that list and create a nested list. So basically add the whole list row of points or points row and append all of that to our self.points. So self.points.append points underscore row. And we can do the same thing for self.states.append states row. And now at the very end, if we print self.points, what we should see is a nested list. So a list of lists, which is basically the list containing all points with a list inside containing each row. So if I hit play, we see it drawing out inside of Rhino, and then we're going to see our print statement in the console log. So we see it print out in our console, and we can see 2 open brackets to start, which indicates a nested list. And if we scrolled through here, we would be able to actually see that there are chunks of lists of exactly array length long. So each list is array length long, and we should have array length many lists. We can check that by saying print length of self.points, and then we can also say print length, not of self.points, but self.points of 0, which is the first row in that nested list. So if I hit play now, and just because we don't want to add these to the document, I'm going to say create point, just so it runs a little bit faster, and it now says 20 and 20. That might be a little bit confusing at first because our array length is the same in both axes, but what it's printing first is how many rows we have, and then what it's printing second is how many items are in each row. So they're the same value because we're looping through with the same value in each axis. So we now have stored all of our points as well as all of our initial states. Now we can go ahead and copy this and comment it out. And then paste down below. So the next thing we're going to do, since we've kind of gone through the logic of these CAs, is actually step into the portion that is going to be different than our 2D CA. And that's going to be, or at least the primary thing that's going to be different, is our render function. So I'm going to make a function, I'm going to call it render, and we need to feed in self. And then we're going to need to feed in some other data, but for now, I'll just close those parentheses and hit enter. So what we need for this render function is we need to be able to convert every single point, so every point that we're drawing out in that point array, into a box. So what is a box composed of, or how can we create a box? Well, we can go ahead and take a look by typing in our render function rs.addBox. What does this take in? It takes in a number of corners, which are a list of points. So the corners are identified by the 8 points that are corners of that box, and it takes in a list of points to identify that. So I can delete that from our Python script for now, and we can still look inside of Rhino, and I'll actually minimize that script while we're looking at the Rhino logics here. So if we wanted to get corners of a box from this particular point, what we could do is move it up 1 unit. So up 1 unit in the X, and then we could move each one of these up 1 unit in the Y. That gives us the bottom square, and then we can move all of these 1 unit in the Z. So one of the points is only moved 1 unit in the X, one is moved 1 unit in the Y, one is moved both 1 unit in the X and Y, and then we have that same amount, but now just also moved 1 unit up in the Z. Then we would feed in all of these points, and we would be able to construct a 3D box or a cube. So if we go into Python, what we're trying to do is translate this 2D grid of points using the render function into a 2D grid of boxes. That way we can visualize in 3D as actual geometry instead of just points. So what we need to start is going to be our entire list of points. So read in list of current points. So we have that stored in self.points. Now what do we need from this in order to do this? We need each point in this list of points. So for point in self.points. And then inside of this, so I'm going to say also loop through each point in list of points. And now inside of this loop, what do we need to do? We need to perform this operation to get the corners and then add a box based on these corners. So for point in self.points, we need to take that point and say corner 1. What does corner 1 equal? Corner 1 equals our point plus some vector, so rs.create vector. What do we need to feed inside of here? 1 unit in the x-axis. So that's going to be 1, 0, 0. So our point plus 1 unit in the x-axis gives us that second point. Now we can copy and paste this for corner 2. And also, while we're at it, we can go ahead and make corner 0, which is just equal to the point, which is that 1 corner point. So we now have corner 0, corner 1, and now we're on corner 2. What is corner 2? Well, it's 1 unit in the x and the y. So we need our vector to be x and y value of 1. And now we can move on to corner 3. What is corner 3? Corner 3 is just 1 unit in the y. So we're going to make our x value 0. Now what are all of the points above? They are just these same corner values. 4, 5, 6, and 7, giving us a total of 8 points as we see in Rhino. And what do we need here? We need plus rs.create vector. Now we could just go ahead and add 1 to this. So we could just say 1, 1, 1, and then 0, 0, 1. And that would be totally fine. Alternatively, what we could do is say we need all of these points just plus this 1 unit in the z. So either way, it's pretty much just as short to do either way, but we could also say corner 0, corner 1, corner 2, and corner 3. And it's not plus that particular vector there, it's just plus 1 unit in the z-axis. So move it all up 1 unit in the z-axis. That gives us our top row, right? As we did, we took all 4 of these and in Rhino moved them up 1 unit in the z-axis. So that's what we're showing here in our code. Now we need, as an input to our box creation, we need a list of corners. What does this list of corners equal? Well, it equals corner 0, corner 1, corner 2, corner 3, all the way down to corner 7. So we can go ahead and paste that in. 1, 2, 3, 4, 5, 6, and then finally 7. We can double check that we don't have spelling errors. 0, 1, 2, 3, 4, all corner, yep, and stored inside of the list corners. Now what do we do with this? We can now create a box. So rs.add_box, input a list of corners. We have our list of corners. Let's delete these points in Rhino. And now what do we need to do to actually run this function? We need to call that particular function. We can call it for now from outside and say myca.render. And we don't need any inputs into this function because we're just using our current self.points. So if I hit play, so it actually wasn't the issue with the point add at all, but we can just go ahead and leave that as it is. The issue is because we're using our nested loops. So if we go back and think about this, I was treating it as though that this self.points was a flattened list. So that's not a point in self.points. So we should really call that something else, maybe like point array. So we could maybe refer to it as self.point array. And then here refer to it as self.point array, self.point array. And we can say for row in self.point array, and then for point in row. And then we need to tab all of this in. What we were doing was getting the entire list from that row, and we were using the list rather than an actual point inside of that row. So now we have a point in row looping through each of those. So remember, I'll say in nested list of points. Read in nested list of current points. So we need to unpack that using 2 loops to iterate through not just each point, but the row and then each point in each row. Now when we click play, this should go ahead and give us each one of those boxes. And it's going to take a little bit of time to think. It's taking time to think for 2 reasons. Poly surfaces are heavier geometry than, let's say, a mesh, so it is going to take a little bit of time to render out each one of these boxes. The other thing is we're redrawing the boxes every single time. So every single time we iterate through, we're adding a box to our Rhino document. How might we change that? Well, we might change that by saying first, enable redraw, and setting this equal to false. This turns off the redrawing of that Rhino display. We can then exit out of our for loops, and then at the very end we can say redraw true. So we're turning it off, saying do not redraw this, and then once we've done the entire loop, so we have the entire array of boxes, then we can redraw it in our Rhino document. So now hit play. So it waits a moment and then draws all of our boxes together. What's another way that we can speed this up? We could, instead of using add box, use a mesh construction. So I'm just going to copy all of this down, comment it all out, and we'll convert this add box to a mesh construction, so a mesh box. Now with any mesh geometry, we actually need to take those points, and instead of just feeding them in as a list of points, we need to build out each individual face. So I'm going to again just draw this inside of Rhino, and we'll make our box. So we have 2 points there, move them in the Y, take those 4, move them in the Z, and now we have our list of 8 corner points. Now how do we make a mesh? Well, what this requires is for us to feed in a mesh, and then we could use, to simulate this in Rhino, a command called 3D face, and we need to go from our 0 point to our 1 point, and then if we're trying to make the face that is closest to us, then we need to jump up and we need to go to the 5 point and then the 4 point, hit enter, and that gives us one face. So that's 0 to 1 to 5 to 4. And then we would need to continue on doing this for each face of the mesh. So we know the first one, so our first face, which we can actually make as a variable here, we'll call that F1. And what we want to store in this F1 are all of the indexes for our faces. So store variable for face vertices. So all the vertex, let's say vertex indices in face. So we're going to have a list of all of the indexes of each one of these vertices. So we have one here, and then we have our corner 1, then we have our corner 5, and then corner 4. So what is face 1? Face 1 is 0, 1, 5, 4, and then that's it. Now, what is face 2? Let's go to face 2. Let's go around the sides first. Face 2 is going to be 1, 2, and then this is 6, and then 5. Enter. So 1, 2, 6, 5. What is face 3? We know that we have 6 faces of our box. So face 3 we'll just do as this next one on the side. And this is corner 2 to 3 to 7 and then to 6. Enter. So 2, 3, 7, 6. Now we have our last one, which actually I'll keep inside of here to finish out the sides. So our last one on the sides is going to be our face 4. What is face 4? Well, it is 3, 0, 4, 7. So 3, 0, 4, 7. Now what are our other two faces? Our other two faces are going to be our top and bottom. So what are those? Well, 4, 5, 6, 7, enter. So we can say face 5 equals 4, 5, 6, 7. Face 6 equals, what does face 6 equal? It equals 0, 1, 2, 3. And you can see that that actually creates, when we do 0, 1, 2, 3, an upward facing face, which is flipped. So what do we need instead? We actually need to go, make sure we're going counterclockwise while looking at the outer side of that face. So not clockwise, but counterclockwise. So 0, 3, 2, 1. Enter. Now we have that face drawn out. So this needs to be 0, 3, 2, 1. Close that out. That gives us our 6 sides of the face, 6 sides of the cube, or 6 faces. Now instead of add box, what do we need here? rs.add mesh. Add mesh, if we open the parentheses, takes in a vertex list, so a list of vertices in this particular mesh box that we're going to use our corner points. What else does it take? Face vertices, which is a list of lists containing which vertex indices related to our corners make up the face in our box. Well, we already have that. We just made that list. So we just need to convert that into a list called faces, which is then a list of lists, and we'll feed in here face 1, face 2, face 3, face 4, face 5, and face 6. So that's all 6 of our faces. The first thing we need to input is our corners as vertices. We can even call these now maybe vertexes, and then feed in here vertexes. And then we need our face indexes, so we can input faces. And then we can just close our parentheses. Now if I delete what we've drawn out inside of Rhino, hit play, we have one closed mesh, which is a closed mesh box drawn out at every single point. And for now, we're drawing them across every single point because we have no rules that any of our points are alive or dead, and we're running the render function for all of them. So we now have our mesh drawn out. So it's a little bit different than structuring a normal box or a surface box or polysurface box, but it's still the same kind of basic structure. Now, instead of drawing them each as separate individual boxes, to run it even faster, what we can do is store every single one of these boxes within a list, which we can just say is a global list called boxes, and we can append to this list of boxes this added mesh. So we can just cut and paste that inside and add that added mesh into our boxes list. Now at the top, we need to actually make that empty list for all of the boxes. And then at the end, what we can do to speed up the rendering of these boxes is join them. Now we can't use join curves, join surfaces, we need to use join meshes. What does this intake? Object IDs. What are we going to give it? Our boxes. And then it says delete input true or false. We can say true. So we just want joined meshes as an output into our document. Now if I hit play, it runs even faster. It's hard to tell, but also all of these boxes are joined. If we didn't want them joined for whatever reason, then we could omit this step. But when we have more complex arrays from our 3DCA, we're going to want it relatively clean. And this is one way of kind of keeping it as one entire chunk. Now I'm going to go ahead and copy all of this, comment this all out, paste below, and we'll get into the next step. So for the next step, we want to actually build our run function. So I'm going to add a function here, and we're going to call it run. We need to feed in self, and then we'll start to pass in information inside of this. So what do we need for our run? Well, just like in the previous portion of this video, we need to input iterations, and then inside of this run function, we need to recursively call to run again for X number of steps. So we can call this iterations, we can call this generations. What do we need to do this? We need a global variable up here. Let's call it generations. We can set this equal to 10 for now. We need to do something with this generations information. What are we going to do with it? We're going to pass it into our run function. I'm going to comment out our render call, and then below this say myCA, call our run function. What are we passing in? We're passing in generations. How do we read this in? We take in some input into our function. So we'll call it _gen. Now, how do we run this recursively? We add a conditional saying if _gen is greater than 0, and then we add a call to self.run. What do we give it? We can give it _gen. In order for it to increment down each generation, we need to say gen -1. So if gen is above 0, increment down each time and call this again. Now, what else do we need inside of this run function? Well, we have our current states and we have our current points. Every single generation, we're going to need to store a next gen and next states, just like we did in the first portion of this video, to be able to temporarily store those values, edit them, and then all together we're going to update the actual values of self.points and self.states. How do we do this? We create variables, which we're going to call next _gen, and we're going to set this at the start equal to self.points. We can do the same thing for next states equal to self.states. Now, our self.points as well, we've now titled self.point array. So we want to make sure that we're using that instead of self.points. So next gen equals self.point array, and our states are still self.states. But keep in mind that self.states are also inside of a nested array. Now, if we are going to run the next step here, what do we need to be able to update this function to run the next generation? Well, we need to save this information back. So we've stored it in a temporary variable. We basically reverse this operation by saying self.point array equals next gen. Then self.states equals next states. So just flipping that back so that we can set that equal to our property stored inside of our class. If we didn't do that, it would just be overwritten each time, and we would actually just stay entirely the same because it would never change the property value inside of our class. So then when we go to render and read in our self.point array, it would never increment relative to our next generation information. So we would see basically nothing happening. So it's incredibly crucial that we do that restoring of those values. Now, we can give ourselves a kind of else here as well if that condition is no longer met, and we can just say else return. So if it's not met, return and exit out of this function. Now we can go ahead and leave that there for now, copy all of these lines, comment them out, and we'll jump into the next step. So in this next step, we're going to build the actual rules for this CA and get it to actually run. Where are we going to do this? We're going to do this inside of our run function. What do we need here? Well, what we need is to loop through every single point in our point array. How can we do that? We can do that similarly to what we've done here. So for row in self.pointArray and for point in row. If we wanted to do that but using the indexes instead of directly calling those names, we can do that by saying for I in range length self.pointArray, close those parentheses. Then we can say for j in range, where I and j become index values, in length self.pointArray. And now we're not going to use the length of the point array itself, but whatever that I index, so that particular row of the point array is. So as we increment through an I, we're going to say this particular value in the point array, or this particular row rather in the point array. And then as we increment in j, we say this particular point in the row. Now, how do we get those as actual points rather than just indexes? We say self.pointArray of I of j. That's going to give us the current point that we're currently at in this array. Once we've actually extracted that, what we want to do here is not get the point itself. We're going to add the incremental steps in our z-axis. So we have the point. What if we want the point in the next generation moved 1 unit up? Well, we can just say add z steps. So some stepped value, and we'll say in the z. So plus z step. What is z step? We can define z step at the top as a global variable, and we can set this equal to rs.createVector. What is the vector? 0, 0, 1. 1 unit in the z-axis. That allows us to have a first generation that is just at the base, second generation that is 1 step above, and each generation it will continue to step 1 step in the z. Now, if we just step, we don't get that actually fed back into our original point array. How can we feed it into our point array? Well, we need to store it in our next gen variable, or our next gen list. How do we store things inside of nested lists? We open them up and then replace that value. So we're opening up our next gen in the row and particular item of this point. So it's the same I and j, and we're placing in there not our current point, but our current point plus the z step. Why do we do that here? We do it here so that we can take the undistorted point, add it into that list, and that way we know that we have those points stored for the next generation and ready to go. That's particular to a CA because in a CA we need that entire point array every single time, and we just change which ones of those points we render. So we're changing which things we're adding boxes to, but we do want every single one of these points. Now, what else do we need? Well, we need a neighbors list. So right now we can make an empty list for those neighbors, and we need n1 equals, and then we can copy this all the way down because we need n2, and then we need n3, n4, n5, and we need all 8 of our neighbors. So it's the exact same as the first portion of this video. So n7 and 8. So 1 through 8 neighbors. What are these equal to? These are equal to not our point array of I and j, which is our current point, but our self.states. And then we would say of I of j. So that would give us our current state. So current state is self.states of I of j. How would we get the next state? Well, if we just want the state to the right first, we can do that here. by keeping our I value the same, but just like the trick we showed in the first portion of this video, we want to use our modulus of length self.pointArray all inside of that index, and that takes care of any stepping over or under the index range of our list. So that's going to basically be the same thing as calling self.states of I, unless our I value is outside of our index range. Now, in this case, we know that it wouldn't be because we are stepping through that length there. So this is maybe overkill to add it when we just have the I variable. So we could also just omit this, but for consistency, I'll leave it in for now. Now in our J, what do we need here? Not J, but J plus 1. And then again, we're going to copy our modulus. And do we need the modulus of the entire point array here? Or should we tailor it to J? Since this J index is related not to self.pointArray, but self.pointArray of I, we actually need here the length of self.pointArray of I. We need the length of that particular row, the modulus of that row. Another way of doing this is to just basically use our array length here. So we could either use self.pointArray, or we could also just use the array length as we did previously. In this case though, this should be perfectly fine. And then we can copy and paste this down. Now what does our N2 need to be? Just J minus 1. So not this point in this row, but the point in this row, so still the same I value, but not this J, J minus 1. Now what do we need for each of these? Well, we need a J plus 1, and then a J, and then a J minus 1. So that's our current point to the right, and our current point to the left. But not in this row, as we've just done here. This time, we need I plus 1, which is the row above. Now if I replace each of these, we've taken care of those neighbors. Then if we copy these down for neighbors 6, 7, and 8, what do we need here? We need the row below, so I minus 1. What do we need for our J? J plus 1, J, and J minus 1. So this is the way that we get our entire list of neighbors. How do we store these into a list? We take that list, place it below, and infill our neighbor values, N1, N2, N3, N4, N5, N6, N7, N8. So all 8 neighbor values stored in this list. Now we step into our cellular automata rules, which again, we're following the particularities of John Conway's Game of Life rules, which I covered in the first portion of the video, so feel free to refer back to that if you need to. I'm going to kind of step through this quickly so that we can reuse that same logic that we've already covered in that earlier portion of the video. So the primary thing was test whether this current state is alive or dead, so is 0 or 1. So we can say if self.states of I of j, so that's our current state. That gives us only the particular points that have a state that is alive. Now, the rules state that if it is alive, and we have a particular number of either alive or dead neighbors. So to do this, again, just a reminder, we need our values for how many alive neighbors and how many dead neighbors, which we start with 0 of each. And then we need to say for I in neighbors, looping through our list of neighbors, if our neighbor, so if our neighbor is alive, then alive plus equals 1. Else our neighbor is dead, so then dead plus equals 1. Now what are our rules? If alive neighbors is less than 2, then not self.states, because we want to store our values inside of this temporary list. So next states of I of j equals, and then we can use a 0 value, so equals 0, or false, or dead. So if we have fewer than 2 alive neighbors, then our current live neighbor dies. If our alive neighbors, so else if our alive neighbors equals 2 or alive equals 3, so if it's exactly 2 or 3, then next states of I of j equals alive. We don't have to state this, as I mentioned in the previous portion of the video, because we're already alive, so it's just keeping it consistent. Now, if alive is greater than 3, so if we have more than 3 live neighbors, then we die as if by overpopulation, so next states of I of j equals 0. If our current state is dead, then we say else alive equals 0, dead equals 0, for n in neighbors, and then we count how many are alive. So if n alive plus equals 1, else dead plus equals 1. And now we test if alive equals 3, next states of I of j equals 1. So if our alive neighbors are exactly 3, then we convert a dead cell into a live one, in John Conway's analogy, as if by reproduction. Then we can say else remain false, or we don't have to say this at all. But in all other cases, it is going to remain 0, which is dead, which it already was. Now, instead of rendering outside of our function or outside of the class, if we want to render this every single time we update here, we're feeding in all of our list of points. What we want to do is say maybe every single time that we run our run, we can go ahead and update our render first. So not my CA in this case, but self.render. And then we can run through all of these and then run. Alternatively, what we could do is place this inside of our updated point arrays. For now, though, I guess we can, yeah, you know what we'll do? We will nest this inside after our update so that we get both the next states as well as the next arrays. And then we can also call this in the constructor function so that we get the first round of them. So self.render after we've created the initial input values. Now in our render function, right now we're rendering every single point in our point array. So how might we change it to only render or only add the mesh to the particular ones that are alive? How do we do that? We say, instead of for row in self.pointArray, we can say for I, row in enumerate self.pointArray, for j, point in enumerate row. And now we can use that to read in our self.states of I of j. So our current state. So if our current state, so if it's alive, nest all of that inside of that conditional. So if it's alive, then render it. Else, don't render it, because we don't want to render our dead cells. And then we're calling it in the constructor, so it will run one time at the beginning with the initial state, and then it will run every single time we jump to the next state after we've updated, and then called to run another generation. We could also place all three of these outside of this conditional if we wanted to keep that last value that we've actually gone through and saved out. So it might be good to just do that so that we can keep those values that we've already run through. So if we keep it outside of our conditional and then we only use that conditional for our run and then to subtract our generations, then we make sure that we're rendering every single one of those generations that we have running. Okay, and now that should be it. So if we go ahead and hit play, what we should see is the boxes being generated, and not only are they generated, but at the very end there we take that whole list of box meshes and we join them into one mesh. If we hit play, we see that incrementing up, and we have 10 generations at a 20 by 20 density. So we're using our array length of 20 and our generations of 10. It's incrementing in steps of 1. And this is just showing us how the generations of the 2D CA are changing over time. If I delete that and change generations to 40, hit play, our 40 generations drawn out. So we now have a stack of a joined closed mesh that is 40 generations or 40 units tall. We can also change the density here by changing the array length. So we could change the array length to 10 to make it smaller. It's going to run a lot quicker. We could now change the generations to 100, and it will run and become a much taller tower. And we'll actually see how that CA or how those CA rules change over time. So we start to see kind of streaks forming. If I change to Arctic view, so we see these kinds of holes forming, and then our meshes being kind of responsive to those, and then infilling at a certain point following the CA's two-dimensional rules. So instead of seeing it flicker on a mesh plane, we actually see it build up in space. So I'm going to move that one over, and then we can come back here and do one at, let's say 20 units. And we can try an even smaller one with 6 units. And you can see in that one, it actually reached a stable state after that many values. So we actually created, I think this is actually a still life. I believe, I mean, if it's staying that consistent for that long, then it's probably a still life which stays stable for ever. So we actually see that stability not referenced in time frames, but referenced as stability in the stack, which is pretty amazing. And if you think about this as a designer, we now get a kind of transition from intricate moments present in this CA stack to stable moments presented as kind of linear elements in the stack. So it looked more chaotic to the left. With fewer iterations, we now see some kind of structure emerging. And if we change this to 8, hit play, again, we see maybe a little bit more kind of clear structure or organization patterns relative to the CAs that we see here on the left. And just like with the other CA example or the LinkedIn's Ant example, the next steps here are how do we make this a multi-state cellular automata? How would we make this actually read not two-dimensional neighbors stacking the generations, but actually make a 3D grid of points and read not 8 neighbors, but we would now need 8 neighbors plus the 9 above and below. So we now need a full set of 9 plus 9, so 18, plus our current 8. So we have 26 total neighbors that we need to search for inside of this three-dimensional grid. Now, we would also have to adjust our rule sets according to that three-dimensional cellular automata, but we can go back and reference additional algorithms to kind of gain some of that insight into which ones work and which ones don't as rule sets or initial states. There's a lot of different things that we can do with these base codes, but this is just a kind of general introduction to get us thinking about how we can use this, both as a kind of formal generator or a texture generator, producing texture on the surface of a mesh. Also, how we can think of kind of chaotic or random motion that eventually produces an emergence in order or a kind of patterning system. So these are really interesting for those reasons. So that's all for our introduction to classes and cellular automata exercise. But please continue to kind of explore these topics and see what you can make with just these basic introduction videos. In the next videos, we're going to get into building agent definitions using classes as well. And then we'll also get into surface-based gradient descent, as well as what's called a mesh crawler or a surface crawler, which is essentially just an agent or a kind of particle that moves on the surface of either a mesh or a surface. You can use either one, and we'll probably do both in that video. So it's an extension of this introduction to classes, which is really exploring how we think about both texturing or operating on surface conditions of existing generated geometry, related to some of our earlier videos more directly on form finding and thinking through geometric volume and space. And here in this particular example, we're also still wrapping that into some explorations in form making and kind of understanding volumetric conditions or spatial conditions through these algorithms as well.